C.3, Laplace transform of derivatives. Yeah. So C.3, C.4, we will derive the formulas, Laplace transform formulas for derivatives, integrals. These two formulas, very important to help us solve ODEs. Yeah. Another powerful tools we need to use when we solve ODEs. Yeah. All right, C.3 first. Point of view of operational calculus. Yeah. Here, high level, yeah, because we learned at the beginning of this topic, yeah, we want to convert ODE problems to algebraic problems. Yeah. So operational calculus to algebraic problems. Yeah. So operations of calculus on functions, yeah, derivatives, integrals, yeah, are replaced by operations of algebra on transforms. Yeah. Transform Laplace transforms. Okay? Yeah. Yeah. So then after you take Laplace transforms, you won't have derivatives and integrals. Yeah. You only have multiplications, division. Yeah. All right. The form, yeah. The formulas, yeah. So these two formulas, yeah. Very important. Yeah. Yeah. All right. Laplace transform of derivatives. Here we calculate first derivative, second derivative, Laplace transform. All right. The transform of the first, second derivatives of little f function satisfy these two equalities. Yeah. Laplace transform of f prime equals, see the first term, s times Laplace transform of little f minus initial value f at 0. Okay? Initial value is used in this formula. Little f of 0. Yeah. All right. Second, Laplace transform of f double prime, yeah, equals, so you have three terms. The first term, you need to use s squared times Laplace transform. Yeah. After that, you need to use two initial values. Yeah. F of 0 initial value minus s times f of 0. Then minus the second initial value, f prime of 0. Okay? Yeah. Yeah. These two formulas very important and very easy to derive. Yeah. So we will calculate, we will derive quickly. Yeah. All right. Formula 1 holds if f of t is continuous for all t greater or equal to 0. Yeah. Continuous. Yeah. That's a pretty weak condition. Yeah. Why Formula 1 holds for f1 is continuous? Because when you take f derivative, in order for f to be differentiable, it must be continuous, right? Yeah. Because if it's not continuous, then it cannot be differentiable. You cannot take a derivative. Yeah. At some point, the derivative is not defined. Yeah. So the continuous, that's a minimum requirement, yeah, for f to be differentiable. Yeah. So it's a very weak condition. Yeah. And to satisfy the growth restriction too. Yeah. Yeah, we wrote that growth restriction, right? So what's that growth restriction? Formula number 2. Yeah. Absolute value of f of t bounded m kt. Right? Yeah. Yeah. In order to make f Laplace transform of f, defined, okay, well defined. All right. F prime of t is piecewise continuous on every finite interval. Yeah. F prime piecewise. Yeah. So if we only look at the first formula, we don't look at the second formula. If we only look at the first formula, then f prime is piecewise continuous, then its Laplace transform, we can consider its existence. All right, yeah. Piece interval, semi-index, similarly, with 2 holds for f and f prime. Okay, yeah. All right, satisfy the growth restriction. Yeah, and there, f double prime. When you look at the second formula, double prime, piecewise and continuous. Yeah. So here, I think, all these conditions together. So it's very easy to get confused. Yeah. Because if you look at the f double prime, for little f, if the f double prime exists, that means f prime must be continuous, right? Yeah. Yeah. If f prime is not continuous at certain points, then f double prime does not exist at those points. Yeah? Yeah. Yeah. Minimum requirement. Yeah. So here you can see f prime is piecewise continuous. Piecewise, you may have some discontinuities. If f prime has discontinuities, then you cannot consider f double prime. Okay? Yeah. So here, you need to know. So the reason is, right, because there is a situation you only apply the first formula, you do not apply the second formula, right? When you only apply the first formula, then you can consider piecewise continuous. You can still apply the first formula. But if piecewise continuous but not continuous, then you cannot apply second formula. Okay? Yeah. The second formula, then f double prime, double prime must exist, and furthermore, it's a piecewise continuous. Then its Laplace transform can be defined. Yeah, can be defined. Yeah, but how about? Yeah, so here. Yeah, yeah, so here. Yeah, actually, the condition here, very complicated. Yeah, to understand the bottom part, the condition part well, so you need to have some very good understanding. Yeah, all right. Yeah, probably after we get more materials, then we can come back to understand these statements again. Yeah. Because at this point, it's not easy to understand these things. Yeah. Yeah. So let me let's get more experience. Yeah. Then we come back to understand these statements. Yeah. Yeah. Otherwise, very messy. Yeah. If you look at the statements at this point, very messy. Yeah. All right, so next we need to derive these two formulas. Yeah. Here you can see differentiation operation in operations of calculus, operational calculus, corresponds to multiplication in algebraic operations. Yeah. Then, similarly, integration in operational calculus corresponds to division in algebraic operations. Yeah. All right. Proof of the derivative formula. Yeah. So, pretty straightforward. Yeah. Not very hard. Yeah. All right. So our goal, we want to prove these two formulas. Yeah. All right. Then, let's start from the definition of Laplace transform. Yeah. Laplace transform of f prime, we just replace, original little f function by f prime function. Yeah. Then, integration by parts. Yeah. So we can do integration by parts. Yeah. Okay. Yeah. All right. So then, yeah. Right. Yeah. How can you see? Yeah, because All right, so here we need to calculate the first term, second term. Yeah. The second term, easy. Yeah. The first term, yeah. We plug in infinity, then plug in 0. Okay? Yeah. Infinity, we take limit. We take a limit. Yeah. All right. So then, yeah. Limit, how can you see? Yeah. Yeah, limit, 0. 0, yeah. 0, you get this term, okay? Yeah. Take limit, now. F of infinity limit, yeah. Yeah. S. Yeah. Right. We know F is bounded by, yeah, think about it. F is bounded. So here you can see there is some condition, right? Yeah. F is bounded by m times e to the kt. All right. Then, for the first infinity, you need s greater than k, right? You need this condition. Then, the first term, when t goes to infinity, then it converges. Yeah. Otherwise, it does not converge. Okay? Yeah. So here you can see so there is a condition. Infinity. Yeah. Otherwise you may have some problem. Yeah. So then, if you have that condition, then you have the first formula. The second formula, yeah. But the second formula, we just apply the first formula, right? Yeah. Because f double prime is the prime of f prime. Yeah. So you take the first formula. Then you replace f prime by f double prime. Then f by f prime. Then f prime of 0. Yeah? But this Laplace transform of derivative, you apply the first formula the second time. Okay? Yeah. Second time. After simplification, you have this. Yeah. So the second formula relies on the first formula. Yeah. Okay? Yeah. Just apply first formula twice. Yeah. 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 But here there is some condition. Yeah. So there is some bound condition. Yeah, we need to check. Yeah. All right. Yeah. But there is approach. Remember, there is one strategy. So when people apply these formulas to find the ODE solution, so they do not worry about, if the condition is satisfied or not. They just do it. Okay? After they find a solution, then they verify it if it's really a valid solution. Yeah. So that's strategy. If people use that strategy, but you cannot skip that verification step. Okay? Yeah. Because if you do not check the condition, then you need to do the verification. Yeah. If you do not check the condition at the beginning, so you need to do verification after you find the solution. Yeah. Yeah. Because after verification, then you are 100% sure your solution is correct. Okay? Yeah. All right. Then this formula we can apply many times. We can calculate the Laplace transform of high order derivatives, nth order derivatives. Yeah, you just apply it n times. Yeah, or you use mathematical induction, right? Yeah, people can use mathematical induction. Yeah, yeah. So here we just apply the first formula. Okay? Yeah. The first formula, we can get that. So another round, first formula the second time, keep doing. Okay? At the end, so we have a nth order Laplace transform version. Yeah. Yeah. In this way, we can use Laplace transform to solve higher order ODEs. Yeah. Because we can apply Laplace transform on any order of the derivatives. Yeah. Okay? Yeah. So you can see, yeah, very powerful. Very powerful. Okay? Yeah. All right. Yeah. The condition still, because there is some condition. Yeah. Because here, checking those conditions, not easy. Right? Yeah. So you need to consider, a lot of factors. Yeah. Just like our previous theorem, the condition part very messy. Right? Yeah. First there was 7 piecewise, very, very messy. So then usually, most people, they do not check those conditions. Okay? Most people, just do it. Okay? Just apply Laplace transform on derivatives, any order of derivatives, and find the solution. Yeah. 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 So after that, because it's very easy to verify if the solution you derived is really a solution. Yeah, very easy to just plug in, right? Plug in into the original formula. Yeah. All right. Yeah. Calculate Laplace transform by derivative formulas. Yeah. Yeah. So here we need to do some examples. Yeah. All right. First, let f equals t times sine of omega t. Yeah. So we have this t times sine omega t. Let's calculate its Laplace transform. Yeah. All right. All right. Let us use 2 different ways to calculate. So you can see how powerful is our derivative formula, Laplace transform of derivative formula. How important is that? First, we do not use that derivative formula. We just calculate Laplace transform directly without using that derivative formula. You can see how hard it is. Yeah. Calculate L of f. Yeah. Let's just apply the definition formula. Yeah. L of f. Yeah. Integration by parts, right? Yeah. Okay. Yeah. So you can write the first step. Yeah. Then integration by parts. Yeah. We write this way. Yeah. Yeah. The good thing is the first term is 0, right? Yeah. It's gone. Okay. After you plug in those 2 integral limits. Yeah. 0, infinity, you take limit. Okay. So at both limit, this term is gone. Okay. All right. But the question is how to calculate the next integral. You have the first one easy to calculate, right? But the second one you have t cosine. The second one not easy to calculate. Although if you do another integration by parts, you can calculate the second one. Yeah. But you need to do another integration by parts. Yeah. Here, I didn't continue. I just let you know, in order to find the answer, how much work you need to do. Okay, that's enough. Yeah. Now, second, I want to show you, if we use the Laplace transform formula for derivative and the second derivative, we can find the answer easier. Okay? Easier. Yeah. All right. This time, let's apply the Laplace transform of second derivative, this formula. All right. Yeah, the f function, f of 0 is 0. Yeah. F prime of 0, we need to calculate. So we calculate f prime function first. Yeah, very easy. Yeah, product rule of the derivative. Yeah, prime function. You plug in t equals 0. You get f prime of 0, also 0. Yeah. Then L of f double prime equals s squared times L of f. Okay? Yeah. L of f. Yeah. All right. But your goal, you want to calculate L of f. Yeah. So at this point, yeah, still we need more information. Okay? All right. Yeah. So what is f double prime? We can calculate the double prime function, right? Yeah. So we can calculate f double prime function, not that hard. Yeah. So let us apply the Laplace formula function, basic formula. Yeah. All right. Yeah. Then, yeah. So by the linearity property, L of f double prime, the first term we apply the formula number 7. Okay, yeah. 2 constant factor out, so we get this. Yeah. Yeah. The second one, yeah, this is f function, right? T times cosine sine omega t. That's f. So omega squared times L of f. Yeah. All right. Yeah. So here you can see for this L of f double prime, we have 2 different expressions, right? Yeah, we have 2 different expressions. Yeah, and these 2 expressions should be the same. Yeah. So let us write these 2 expressions must be the same expression. Then we can solve this equation for L of f easily. Okay, yeah, L of f equals 2 omega s over parenthesis s squared plus omega squared, parenthesis squared. Yeah. See? You can see, using Laplace transform, yeah, we can find, this property. Yeah, we use this formula, a little easier, right? Yeah, although a little tricky. Yeah. So you need to practice. Yeah. So you need to, make yourselves familiar with this kind of calculation. Yeah. Yeah. So represent the same thing in 2 different ways. Yeah. In math, we apply this method frequently. Yeah. The same expression, but we have 2 different expressions. Yeah. 2 different representations. Yeah. Then we just, connect them. Yeah. All right. So this example. Yeah. All right. C.4. Laplace transforms of integrals. Yeah. Yeah. All right. Yeah. Let's derive the formula. Yeah. So differentiation, integration, we know, so inverse each other, right? So these 2 operations we treat as these 2, they are inverse each other. Yeah. All right? Reverse or inverse. Reverse, okay? Yeah, reverse. All right. Multiplication, division, also, reverse, some, that kind of relationship. Yeah. All right. Then, our goal, yeah. So this time, we have a g function that is the integral of f function. Yeah. Because we want to calculate Laplace transform formula for integral. Yeah. So the function inside Laplace transform should be an integral function. Yeah. Here, we assume this integral function. All right. Then, what's the relationship between f and g? Little f and the little g. Yeah, there is relationship, right? Yeah. The relationship is f of t equals g prime of t. Yeah. Yeah. F function equals g prime of t. Yeah. Yeah. That's from the fundamental theorem of calculus, right? The first. Yeah. Yeah. The first fundamental theorem of calculus. And from there. Okay? Yeah. So we have this formula. Existence, yeah, then. How do you know the Laplace transform of g function exists? Yeah? Yeah. So the existence, first we assume existence of f function, Laplace transform of f function exists. So we have that condition. Then we look at existence of, yeah, so look at it, yeah. So g, yeah, g, like that. Yeah, so g, yeah, m, right. Yeah, but this one, yeah, this one, yeah, all right. Yeah. So we estimate here with the bound of f function. Now we want to estimate the bound of g function. So bound of g function, we get that expression. But that minus 1, we can omit. Okay, yeah, minus 1. So that term. So we know that e term times kt. Yeah, yeah. If kt is positive, e to the kt is greater than 1. Okay, yeah. All right. So we take. Yeah. So we can simplify. Yeah, the minus 1. We omit that minus 1 term. Yeah, simplify. So you can see the g function is bounded by, certain constant multiple of e to the kt. Yeah. Then this form tells us Laplace transform of g function exists. So we can apply Laplace transform on this g function. Yeah. All right. Yeah. To apply that, remember we have that derivative formula, right? Yeah. So here, because, yeah. So based on this formula. Yeah. So we have that derivative formula. So L of g prime, we can apply our first derivative formula. That's this. Okay? Yeah. All right. G of 0, what's G of 0? G of 0, you replace this t by 0, it's 0. Okay? Both upper and lower limits of the integral the same. So G of 0 is 0, so that term is gone. This term is gone. Okay? All right. So you only have s times Laplace transform of g function. Okay? Yeah. Then, so you have the final formula. So here you can see, this formula is, the structure, very simple. Yeah. Very simple. Yeah. You take the derivative of a function, yeah, the Laplace transform, just the s times Laplace transform of its original function. Yeah. So simple. Yeah. But after that, you go back to integral. Because the g function is integral, right? So here, this is the g function, g of t. G function is integral, okay? G function equals, you need to divide s both sides. So that's why you have 1 over s. Then, Laplace transform of little f, that's capital F. Okay? Yeah. So that's the first formula. The second inverse Laplace transform derived from the first formula. Okay? Yeah. Yeah. Sorry. Yeah. So you can see, yeah, we derive that Laplace transform of integral. Yeah. Integral here. Okay. Yeah. Yeah. Right. Then inverse, so integral here. Inverse here. Yeah, excuse me. Yeah. Yeah. All right. So we get the important formula. It's simple, yeah, but very useful. Yeah. But we need to practice. Yeah. Derivative, integral, then Laplace transforms. Yeah. These two formulas we need to practice. Yeah. All right. Example for inverse Laplace transform. Yeah. All right. So here we use this formula. Yeah. Laplace transform of t equals 1 over s squared. We derived it before. All right. Calculate inverse Laplace transform of 1 over s times parenthesis s squared plus omega squared. Yeah. Yeah. Based on our experience, yeah, s, yeah, 1 over s. When you see this 1 over s, sounds familiar, right? Yeah. So you need to get that integral formula. Okay. Yeah. Yeah. All right. So here, yeah, we need to calculate these two. Yeah. Yeah. But when you have that division by s, you can connect to that the previous formula. Yeah. That's formula. 1 over s. You can see this is 1 over s. Okay? Yeah. Yeah. All right. So you need to find a capital F. Capital F of s. Yeah. All right. To find that, yeah, yeah, by that formula, yeah, because here you separate. Okay. All right. So this part, f of s. Right. F of s. Can you find the little f? Yeah. Because f of s is known. Can you find the little f? Yeah. This formula. Remember? Yeah. I need to give you that formula. Yeah. So yeah, f of s equals that. Remember that sine formula, sine omega t, Laplace transform of sine omega, yeah, number 8. Yeah. Remember that. Yeah. So we can find a little f easily by formula number 8. We can find little f easily. Yeah. You can see the difference is at this omega. Here it's 1, that omega. So you divide it by that omega, you can find little f. Little f. All right. So here, the inverse Laplace transform of this expression equals sine omega. Then you divide it by omega both sides. Right. So little f function equals, you divide it by both sides, it's this function. Okay? Yeah. So you apply our basic formula, you can find little f function. Yeah. Then, little f function is known, you can calculate this integral, right? Yeah. Because based on our formula, you need to, in order to find Laplace transform, yeah, you need to calculate this integral. This integral is easy to calculate. Okay? Yeah. So you can find integral that. Then you'll find the first inverse Laplace transform. Then the second. Yeah. Second, you can see, can you use the result of the first formula to calculate the second? Because you divide it by another s, right? Yeah. Yeah. Divided by another s. Yeah. All right. So here we apply that same formula. Yeah. Inverse, it's an integral, but this little f is different. Yeah. That little f is different because this time capital F is this function. Yeah. And capital F is that function the little f can be calculated, right? Little f, yeah, this is a little f. Little f corresponds to that capital F. Okay, yeah. All right, yeah. So we already, from our previous result, then we take integral on this little f. Integral on this little f. Yeah. So this one equals integral. Yeah. This integral is easy to calculate, right? Yeah. All right. Yeah. So you get the answer. Yeah. Yeah. Look, yeah. After these two examples, yeah. So you need to, you know, think about. So what's the usual ways we use to calculate inverse Laplace transform? Yeah. Look at the structure. Yeah. The structure, you know, can you use this formula to help you decompose the function? Yeah. 1 over s times f, some f function. Yeah. F function, can you find its inverse Laplace transform? If you can find, then you have that little f function, then you need to calculate the integral on that little f function. Yeah. Okay? Yeah. Yeah. Look at these examples. Yeah. Yeah. You need to do some calculation. Yeah. 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 Here you can see, other than algebraic operation, you need to calculate integral. You need to calculate integral here. Yeah. All right. Yeah, so the final result, so this way, actually, I want to give you a different, yeah, so this is a different solution, okay? Yeah, because above, we already find a solution, okay? Already find a solution. But sometimes we may have more than one method to find a solution. So this lower part, I decompose the structure inside the parenthesis in a different way. Yeah. Partial fraction way. Yeah. So you know partial fraction, right? So I do the partial fraction decomposition. Yeah. Then I get this formula. Okay? Yeah. Get that formula. The first term we can apply formula number 2. Okay? Yeah. Formula number 2. The second one we can apply formula number 8. See? Yeah. So this is another way. This way simpler. You can see this way simpler. Okay? Yeah. 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 Yeah, because yeah, we get the same answer. You can see we get the same answer. Yeah, but much faster. Okay? Yeah. So the second one, this solution, you need to, you know, try to get used to. Yeah. Think in this way. Yeah. Decompose. So you have a fractional expression. When you have a fractional expression, yeah, so you can do some decomposition like this. Yeah. After decomposition, you just apply the basic formulas directly. You can see this way you do not need to calculate integral, right? Yeah. The first way you need to calculate integral. Okay? Yeah. The capital F, little f, then you calculate the integral. Yeah. And the bad thing is actually, yeah, think about the bad thing. Think about if I only give you this one, you do not need to calculate the first one, okay? I ask you to calculate inverse Laplace transform of this function directly. Yeah. All right? If you do not use this method, okay? Yeah. This is a, you know, highly efficient method. If you do not use this method, think about how do you calculate? You need to calculate this first, right? Yeah. Okay? You need to calculate that first. Yeah. Then, after that, you need to calculate, second round. The first round as the intermediate result, okay? Because second round, you need to use that intermediate result to calculate second round. Look at how much work you need to do. Right? Yeah. How much work. So now you can see this last method much more efficient. Yeah. So get used to. Yeah. Although the first method, you need to know, how to do it in that way. Yeah, because that Laplace transform of integral, that formula is a powerful tool. Yeah, so you want to use that tool sometimes. Okay? Yeah. So that tool is very valuable. Yeah. Yeah. All right. So you want to put that tool in your pocket, okay? In your toolbox. Yeah. But for this question, this bottom method, much better. Especially in your test. Think about in your midterm, right? If you use the upper way, you need to spend a lot of time to do the calculation. Okay? The bottom way, you can save at least 5 minutes. Okay? Yeah. Think about that. Yeah. Yeah. Our second homework assignment, we need to do a lot of calculation like this. Okay? Our second assignment. Yeah. First assignment, yeah. So you have a lot of work to do. Okay? Yeah. So many questions. Yeah. Yeah. So you need to, work very hard. Yeah. First, homework assignment. Yeah. Question?
So we got the second assignment, and then we get the midterm after the second.
Yes, after second. Yeah.
So the midterm will only be everything covered through the first assignment, the second assignment, the test as well.
Yes. But
Or is there anything new that won't be on the 2 that will be on the midterm?
new after second month possible, yeah, because we still have some material possible, yeah, but not too much, yeah, not too much, a little bit, yeah, after second assignment, yeah, 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 we still need to, yeah, otherwise we, yeah, yeah, basically, yeah, let me see, yeah, yeah, okay, basically. Module 1 to 3, yeah, 3 modules before the midterm, yeah. But it's possible we may not, yeah, 2.5 module, yeah, probably we couldn't, if we couldn't complete module 3, yeah, halfway of module 3, then we do midterm, yeah, yeah. I just estimate, yeah. All right. Yeah, so only a few minutes. Yeah, let me see if I have enough time just do one example. Okay, solve IVP by Laplace transform. Yeah, at least we can solve one, right? Yeah, because the first one is pretty simple, pretty straightforward. Yeah, let's solve one IVP problem by our Laplace transform formulas. Yeah, new formulas. Yeah, all right. Yeah. So the equation, yeah, the general. So here, the general way, it's pretty straightforward. Yeah, so here, let me give you the general way. To solve, we leave next time, okay? So for this general IVP problem of second order linear ODE, let's apply Laplace transform both sides. Yeah, all right. Yeah. So Laplace transform, yeah. So here we use these 2 formulas. Yeah, these 2 formulas. Okay? Yeah. But we replace f function by y function. Okay? F function by y function. Yeah. All right. Then, yeah. So let's apply by the linearity property. Yeah. Laplace transform of each term. Yeah. Each term. So we get that. Okay? All right. Right-hand side, Laplace transform of little r function, we use the capital R of S function, okay, yeah, to represent its Laplace transform. Yeah. We assume we have that function, okay. we can find that function. Then, left-hand side, we apply these two derivative formula directly. Okay, yeah. The first, the second, brackets. Yeah. Yeah. Then, all right, it's the Laplace transform part. L of y, we use one function, capital Y function. Yeah, people use the capital Y of S function, capital Y of S to represent Laplace transform of little y function. Okay, yeah, yeah. All right. So then you combine the terms, yeah, and you have k0, k1, yeah. So yeah. Then you can find the capital Y of S function explicitly. Yeah. Because this is all right-hand side function, all known. Okay? The right-hand side function, all known. Yeah. Capital R function, capital K, 0, K1, little a, little b, all known. Okay? That means the Laplace transform of your Y solution is known. You just calculate the inverse Laplace transform. Little y of t equals inverse Laplace transform of the capital Y function. Yeah? See? You find a solution. So this IVP problem, you can use the standard way to solve it. Okay? Just each step you calculate carefully. Okay? Yeah. Do not make any mistake. Yeah. Carefully, yeah, following, standard way. You can find a solution. Yeah. So you can see, yeah. All right, yeah. So let's stop right here. Yeah. So next time we will complete quickly 2 examples. After 2 examples, so we can complete, this part C. So that we start part D next time. Yeah. All right, that's it. Yeah. So this week still, yeah, because you have a lot of work for homework assignment number 1. Yeah. So this week, I do not assign you any new assignment. Okay. Yeah. So let you focus on homework assignment number 1. After homework assignment, I will give you a second quiz. Okay. So after second quiz, I will give you a second homework assignment. Yeah. So then we will do midterm. Yeah. 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 Oh, probably. Yeah. So probably after second assignment. Yeah. So let's see. Yeah. Probably very little new material. Yeah. But I cannot say no new material. Okay. But very little new material.